So next up, we have Stephen Schmidt from Johns Hopkins University, and we'll switch towards hot Jupiters.
Yeah.
Take it away.
Thank you, Dan. Hi, everyone. I'm Stephen Schmidt. I am a third-year PhD student and NSF Graduate Research Fellow at Johns Hopkins University. And today, I'll be talking to you about how I've calibrated the relationship between age and velocity dispersion in the solar neighborhood, and how I've used that to gain some insight into the formation mechanisms for hot Jupiters. So getting started, there are lots of different types of ways that exoplanets evolve and change over time. Some of these happen on a very quick time scale, like disk-driven migration, whereas others, like tidal in-spiral, take billions of years. If we want to get an idea of how all of these different things shape the exoplanet population that we see, we need precise and accurate age inferences for all different types of stars, especially mature field stars, like most exoplanet hosts. However, we run into a problem. Most of the methods that we have for age inference are not very good for mature stars. So like lithium depletion and activity indicators and gyrochronology work for varyingly young stars. Things like asteroseismology end up not being available to use for most exoplanet hosts. And in the case of isochrones, unless, as we heard yesterday, you have a precise JWST transit, the uncertainties tend to be too big to be useful for these precise ages. So we turn to population-level statistical methods to get at what's going on with these different exoplanet populations. One of the ways that we can do this is with the velocity dispersion method. This takes into account the way that stars form and interact with the galaxy they're in. So starting out, stars in the thin disk form very close to the midplane. They take up a very small volume of phase space. And over time, they experience random kicks due to things like giant molecular clouds in the galactic bar. And as a result, over billions of years, their velocities become a whole lot more varied and all over the place. And the measure of how varied these velocities are, their velocity dispersion, can tell you how old it is because, as we can see here with the calibrated age-velocity dispersion relation for the solar neighborhood, it's a monotonically increasing function of age. Now, the way that I did this is I took a sample of about 125,000 subgiants in the solar neighborhood with precise, like 9% uncertainty ages and metallicities as well. And I just did a moving window of increasing age and calculated their velocity dispersion. You can see, let's see, here we go. Yep, there is actually a 1 sigma uncertainty range in like light gray on here. So that's great, but one of the issues with hot Jupiters is that they tend to be more metal-rich. And so because not every star is metal-rich, we want to select the ones that are to make a good comparison. So we do that. And you should know that this isn't a big effect for the typical range of ages for hot Jupiters that we see with this. But either way, we have this. And so when we calculate the velocity dispersion for some population of exoplanet hosts, we can then compare it to this age-velocity dispersion relation. And we can get what we call a characteristic mean age for that population. Now, this is great and fine. But if we're thinking about hot Jupiters in particular, we have to take into account some of the biases that are present in that population. And you can see this pretty nicely with the population of longer period Jupiters, which are on the older side, as you can see here. And this is in part due to the fact that most of them are detected via the radial velocity method. And so, as you may know, this method preferentially selects for stars that are quiet and therefore old, and this is in stark contrast with ones that were not discovered by radial velocity. So, to make an apples-to-apples comparison, we're going to use transiting-only hot Jupiters, and from these, we end up with the period distribution for them. Now, it is thought that high-eccentricity migration preferentially puts hot Jupiters into this period peak. So if we want to get an idea of how this peak is behaving in terms of its age compared to other subpopulations, we might want to try and split it into like thirds, like the peak and then inside and outside the peak. But we run into another problem, another bias, That being that the probability of observing a hot Jupiter decreases the further away it is from its host star. So what we can do is we can weight these hot Jupiters based on this scaled semi-major axis and debias the hot Jupiter population's period distribution to get 3 subpopulations. One inside the peak in light blue, one near the debiased peak in dark blue, and one outside the debiased peak in green. And so with all of these, we can go ahead and calculate their velocity dispersions and compare it to the age-velocity dispersion relation. Now, for the ones outside the peak, these ones are young. I mean, it's expected that hot Jupiters have a cold velocity dispersion. But when we look at the ones near the peak, those ones are a bit older than that. And for the ones that are inside the peak, we find that those ones are a little bit older than that, but like not really too much. Now, we also took into account some other biases that are present in this population, and we found that the age bias incurred by that is no more than 310 million years. Now, thankfully, since this age offset that we find here is around like 500 million years, this means that what we're seeing is something physical, at least partially. Which brings us to the question, how did we get here? What combination of formation mechanisms have led to these subpopulation ages that we now infer for the debiased subpopulations in the hot Jupiter distribution? So broadly, we can divide these different methods of formation and evolution into a early time disk migration mechanism that sort of is agnostic to the period it drops its hot Jupiter off at. And we can think of that as mostly uniform, approximately. We've got this late time migration mechanism that preferentially populates the peak. And we also have tidal in spiral that brings hot Jupiters closer to their host stars and destroys the ones that are closest in. So this isn't something new or anything like that, but because we have these subpopulation ages, we can now gain some more insight into how these combine to create the population we see. So thinking about some different scenarios that we might have for the hot Jupiter population, on the y-axis is the characteristic mean age, by the way. So if you just have disk migration, you don't have very much tidal in spiral, and these hot Jupiters all just kind of stay mostly where they are, pretty much with a very high stellar tidal quality factor, you would probably expect that each of these subpopulations ought to be pretty similar in age, because there's nothing really that's like moving them anywhere, and they all kind of form just randomly, uniformly in period space. Now, if you add tidal evolution to this, the ones that are closest to their host stars get destroyed, and the ones that are a bit further away move inwards. And so you're cutting out all of the oldest ones in the closest subpopulation, but not really for the older ones. So you expect that one to be the youngest. Now, if you have this peak populating mechanism, then you'd expect, since those ones would bring in hot Jupiters at an older age, that middle population where the peak is would be the oldest, and the ones in the subpopulations inside and outside the peak, that it would depend on how that peak is formulated and where exactly it is. But if you add tidal decay to all 3 of these, you would see that the ones that are near the peak would be moved inwards a bit. The ones inside, and so that would repopulate that inner population and allow those ages to be similar to each other, whereas the ones outside the peak would not really have this happening to them. So broadly, we've got essentially 4 different things that could happen for a hot Jupiter. And so to preface this, this is a self-consistent model for the tidal evolution of an exoplanet system. As a function of age in years on the x-axis, we've got from left to right the orbital period as a function of days. We've got the stellar obliquity, and we've got the rotation period. So the hot Jupiters that arrive closer to their host stars via disk migration get destroyed. The ones that arrive further away don't. The ones that arrive via this other peak populating mechanism arrive in the middle somewhere, and then they experience obliquity damping that ends up bringing them closer. like potentially putting some of them in the inner population. And then the ones that formed via disk migration in the middle would also be brought inwards, but not quite enough to be completely destroyed. So if we take all of these different scenarios and create a bunch of different ones of them and create a parametric forward model to kind of describe the hot Jupiter population, ideally what we want to see is something that replicates this. This is the observations that we have, the period distribution for hot Jupiters, and the characteristic mean ages that we see for the hot Jupiter population. And so, if we have, with certain types of tuning parameters, such as a moderate Q star stellar tidal quality factor of 10 to the 6, and then 4 and 5 hot Jupiters arriving in the peak later due to that other mechanism, then we find that we are actually able to more or less get close to what we observe. So, in summary, I have this new method that we can use to get absolute ages for exoplanet populations via the velocity dispersion method in the solar neighborhood. Not only that, but hot Jupiters that are near and inside the peak are older than the ones outside the peak, and the ones inside the peak are slightly older than that. And if you combine some early time, uniformly distributed, maybe disk migration mechanism, and some late time peak populating migration mechanism, you can replicate the subpopulation ages we infer with tidal decay. Thank you all. I have a poster in the poster hall over there, and I'm happy to talk about that too later today, but I'll take any questions. Thank you.
Thanks very much, Stephen. Time for questions. Let's see, start on the left. No? Okay, it's going somewhere else.
Oh boy.
Elizabeth, start. Yeah, go ahead.
Yeah, thank you. I'm Elizabeth Newton, Dartmouth College. I was wondering if you could tell us a little bit more about the age velocity dispersion relation you used. Which one, and did you assume that there was any kind of intrinsic scatter in that? It looked so very precise.
Yeah, so let me go back to that real quick. Let's just go to this one so that it's quicker. Yeah, so in terms of, in what way, with intrinsic scatter? Because I guess the way that I do this is bootstrap resampling of the stars in the window to try and see, I guess that's where we get the 1 sigma uncertainties for it. So I guess we don't assume that there's any intrinsic scatter in there, but we do use bootstrap resampling to try and get at the 1 sigma uncertainty range.
So I'm thinking one of the classical ones is the Whelan relations, and that's I don't remember, some linear equation. Is any population of stars with a velocity dispersion of 40 kilometers a second, does that always have an age of exactly 4 gigayears, or could it plausibly have an age of anywhere between 3 and 5 gigayears? Not because of small number statistics, but because of the intrinsic scatter in the processes that are producing these increasing velocities with age.
Right. So I guess an important thing with this is that you cannot use this to get the individual age for a particular system. I think that depending on what sample you use, you might get a somewhat different result. But I think that overall, the main thing that we're looking for is the arrangement of the different subpopulations and whether or not those differences are large enough to potentially be due to something other than a bias, if that makes any sense.
Okay, let's move on the left. Ankarat.
Yeah, hi, Ankarat from UCL. Thanks for this talk. It's been great to hear so much stuff about ages and planets in this meeting. It's a similar question, but I'm not advocating, I think, for isochrone ages on an individual star basis. But do you think that this is a broad trend that could possibly be probed if we tried to get the best homogeneous isochrone age sample that we could for a sample of hot and cold Jupiters or hot Jupiters and had a look at the average age distributions of those? Do you think that would be a plausible thing to do and try and compare?
Yeah, so I think that would be really cool to do. One of the things that Zafar mentioned yesterday about using JWST transits to get precise ages is something that I think about a lot to try and see like how these are connected. But that is a thing that I am very interested in knowing. So yeah, that would be a great extension of this in the future.
Okay, let's wrap it up here, and thanks, Stephen, again.